Imagine it's a Tuesday afternoon. You're monitoring fires. API P99 just crossed 4 seconds. The support queue is filling up. You log into the database host, and there is Postgres, consuming every CPU core it can reach. You open pgstat activity and count 47 active backends. Some are waiting on locks. Some are waiting on data reads. A few are just sitting there, idle in transaction, holding row locks nobody told you about. And your first instinct, be honest, is to reach for the configuration file and start moving numbers. Maybe raise shared buffers. Maybe restart the service and hope. I have been in that room. And I am telling you, that instinct is the most expensive habit in database operations. What I want to give you in this session is the method that replaces that instinct. Dr. Ibrar Ahmed will walk you through a disciplined, evidence-first approach to Postgres performance. We are going to cover everything: how to build a benchmark that actually means something, how to classify the bottleneck before you touch a single parameter, how to read a plan the right way, how to design indexes from query shape rather than table shape, how to budget memory safely under concurrency, how to tune checkpoints and write-ahead log pressure, how to keep vacuum healthy, how to handle locks and bloat, how to pool connections properly, and how to do all of this safely in production. By the end of this hour, you will have a repeatable method, one you can apply the next time the pager goes off at 2 in the morning. The diagram on this slide is the entire session compressed into one picture. Baseline, benchmark, diff, profile, hypothesis, canary, validate, rollback. Notice it is a loop, not a linear checklist. That matters. If your canary does not confirm the hypothesis, you go back and profile again. You do not push forward with a change that the evidence is not supporting just because the change felt right. The most important discipline in Postgres performance work is this: prove the bottleneck before you touch a parameter. I know it sounds obvious when I say it out loud. But under the pressure of a production incident, frustrated stakeholders, active pages, everybody watching, it is genuinely difficult to slow down and demand evidence before acting. The bottleneck classes on the right side of the slide are the decision tree. CPU saturation, I/O pressure, lock contention, and memory spill each have completely different root causes and completely different safe fixes. A lock problem does not get better with more memory. An I/O problem does not get better with a bigger connection pool. A CPU-bound workload does not benefit from relaxed checkpoint limits. When you know the class, you know which tools to reach for. And knowing the class comes from observation, from statement statistics, wait events, plans, and storage metrics. Not from intuition. Here is something I have noticed in teams that struggle with performance work: they do not have a baseline problem, they have a definition problem. When I ask for a baseline, I get a screenshot of a dashboard from this morning. That is not a baseline. A real baseline is a time-bounded evidence package: P95 and P99 latency, throughput, error rate, top statements by total time and mean time and temp blocks, lock wait counts, dead tuple growth, freeze age, checkpoint messages, and storage latency percentiles, all from the same window, under the same workload shape. Reset statement statistics before the run. Document the client count, the data volume, the connection count, and whether the cache was warm or cold. The code on this slide shows the exact snapshot query. Run it before the change and run it again after. The comparison has to be clean. If you compare a 5-minute window after your change to 3 weeks of accumulated statistics before it, you have not proved anything. You have just made a graph that agrees with whatever you wanted to believe. And that is the kind of evidence that gets teams into trouble, because the next change gets made with the same overconfidence, and eventually you run out of luck. Defensible before and after numbers are what let you ship tuning changes safely. This lab is where almost every Postgres performance investigation should start. pgstat statements is your first and most powerful triage surface. The 3 most important sort orders are total execution time, mean execution time, and temporary blocks written. Run all 3 before you form a hypothesis. Sorting by total time tells you what is consuming the most database capacity overall. Sorting by mean time tells you which individual calls are expensive. Sorting by temp blocks tells you which queries are spilling sort or hash work to disk, which usually means either an access path problem or a memory problem. Bring these three views together before you decide which query to fix first. Now here is the expert nuance. A query with a mean latency of half a millisecond can still be your biggest problem if it runs 20 million times a day. And a report that takes 12 seconds and runs 4 times a week might not be worth touching at. The right question is not which query is slowest. The right question is which query's improvement will move your service objective the most. Also pay attention to rows, shared reads, and temp writes together. A query that reads 10 million rows and throws away 9 million of them in a filter is not a memory problem, it is a predicate or index problem. Those are fixed differently. Once you know which query to focus on, explain analyze with buffers is where the real diagnosis happens. This command turns a slow query from a mystery into a story. The story is told in 4 dimensions: row estimates versus actual rows, how many blocks were read from shared memory versus disk, how many temp blocks were written, and which node in the plan tree actually owns the runtime. Work through the plan from the most expensive node down. If you see external merge and disk usage in a sort, you have spill. If you see a high ratio of actual rows to estimated rows, you have a statistics problem. If you see a seek scan where an index scan should be, you have an index or planner problem. The lab on this slide shows the before and after story clearly. The slow plan spills, reads heavily, and takes over 800 milliseconds. The fixed plan, after adding a targeted index, removes the sort node entirely, reduces shared reads, and runs in 30 milliseconds. That is a structural fix. And it is better than raising memory, because it helps every session that runs that query, not just the ones that got lucky with timing. One important caution: explain analyze executes the statement. Never run it carelessly on a write query in production, and always use realistic bind values. A plan from an unrepresentative dataset leads to the wrong index. Wait events are the branching point. Before you decide what to fix, you need to know why sessions are blocked. pgstat activity gives you the raw signal, state, wait event type, wait event name, query age, and query text. The interpretation is where experience matters. If you see many sessions with wait event type CPU and no wait event, your workload is compute bound. Reduce the work, reduce the active backend count, or improve parallelism depending on the query type. If you see data file read, you have cold blocks or a poor access path. If you see lock or LW lock, you have a contention story that needs its own investigation. If you see client or client write, the problem may be outside the database entirely. The discipline here is to resist acting before you have classified the wait. I have watched very experienced engineers add an index to fix a lock problem. The index made the wrong query slightly faster and did nothing for the lock hold time. I have watched teams raise workmem to fix an I/O problem caused by a sequential scan. The memory change was invisible because the scan was the bottleneck, not the sort. Classify the wait class. Then and only then, choose the right tool. Index design is an access path problem, not a column coverage problem. The question is not which columns appear in this query. The question is, what is the exact path the executor needs to take? For the example on this slide, the query filters by tenant, filters to open status, orders by creation time descending, and needs a small number of columns. A well-designed index mirrors that shape exactly, tenant equality first because it is the most selective predicate, creation time in the sort direction so the executor does not need to sort, a partial predicate to exclude rows the query never wants, and included columns to allow an index-only path when visibility allows it. That single index can turn an 800 millisecond query into a 30 millisecond query without touching any configuration file. After you create the index, validate it properly. Run the plan again. Did the sort node disappear? Did shared reads drop? Did the execution time actually improve under production load, not just in your test? Then check the right side. Every index you add is maintained by every insert, every update that touches those columns, every delete, every vacuum pass, and every checkpoint. On a table that receives 10,000 writes per second, an unnecessary index is a real cost. The best index strategy is always the smallest set of precisely designed indexes that covers the actual workload. The two patterns on this slide exist to solve a specific problem: the hot path that only ever touches a subset of data, or that searches by a transformed version of a column. Expression indexes let you index lower, email, or date_trunk today, or any stable function of column data. When your query uses the exact same expression in its predicate, the index becomes available. Partial indexes let you build an index that only covers the rows that matter: open jobs, ready events, active orders. Those indexes stay small, fit in cache more easily, and cost less to maintain than full table indexes. But these patterns have an operational discipline requirement. When the product changes the predicate, when open orders becomes a different status code, or when the query drops the lower email lookup, the index becomes dead weight. It still gets updated on every write. Track your index scan counts. Review overlapping definitions. If an index has 0 scans in 30 days and the table receives constant writes, drop it. The correct question when you are adding a new index is not "could this help?" The correct question is, which existing index can I remove at the same time? Sort and hash spill is one of the most commonly mistuned problems in Postgres. You see external merge in the plan, you see gigabytes of temp files in the statistics, and the instinct is to raise work MEM. Sometimes that is the right call. But it should never be the first call, because work MEM multiplies silently. It is per sort or hash operation, per parallel worker, per active backend. If you have 100 active sessions and each one of them runs a query that does 3 sort operations, and you raise work MEM from 16 megabytes to 200 megabytes, you have just increased potential memory pressure by a factor of 12. That can turn a slow system into an unstable one. Work through the spill decision ladder in order. First, prove it is spill, get the plan with temp bytes. Then check whether it is isolated or widespread, look at database level temp statistics. Then ask whether the spill can be eliminated structurally. Can a better index remove the sort entirely? Can the predicate be made more selective before the sort? Can the query return fewer rows? If after all of that the answer is still memory, then raise it locally. Use a row level setting or a session level setting first. Prove the behavior under realistic concurrency before touching the cluster default. The most dangerous thing about memory parameters in Postgres is not the individual values, it is the multiplication. The formula on this slide is the one I ask every team to internalize before touching a memory setting: active connections, times plan operators, times work MEM. Add parallel workers and the number grows faster. That is why a work MEM setting that looks safe in isolation can cause out-of-memory events under peak concurrency. Shared_buffers sets the Postgres buffer pool size and interacts with the operating system page cache. Effective_cache_size is a planner signal, not a memory allocation. Maintenance_work MEM controls vacuum and index build operations and should be sized with your maintenance concurrency in mind. The test protocol matters as much as the value. Use set local inside a transaction for a quick proof. Use a role level setting to test an endpoint specific change before promoting it globally. Combine the memory change with a concurrent load test, not just a single isolated query run. And monitor the right signals: temporary bytes, resident memory growth, swap usage, and out-of-memory events. A memory configuration that looks great in isolation but causes instability at peak traffic is not a performance improvement, it is a time bomb. Commits and checkpoints are two distinct write pressures that share the same storage path. A commit needs to flush the write-ahead log to satisfy durability. A checkpoint needs to flush dirty data pages to the data files. When these line up with peak workload activity, P99 write latency rises and user-facing transactions feel it as commit stalls. The spike in the diagram is not theoretical. I have seen it in production systems where the checkpoint timeout was too aggressive for the storage subsystem, and every 4 minutes there was a write latency cliff that showed up in the APM traces as unexplained database latency. The parameters max wall size, checkpoint timeout, checkpoint completion target, and wall compression need to be tuned together against your specific recovery time objective, your disk headroom, and your observed write latency percentiles. The log message about checkpoints occurring too frequently is a useful clue, but it is the beginning of the investigation, not the end. Check storage I/O utilization during that period, look at P99 write latency during checkpoint windows, and verify you have enough disk headroom before simply raising limits. Raising limits to hide a storage capacity problem just moves the incident forward in time. AutoVacuum is one of the most underestimated performance systems in Postgres. Teams treat it like background noise, something that runs on its own and rarely needs attention. Then one day they discover their orders table has 18 million dead tuples, last auto-vacuumed 7 hours ago, and every sequential scan is touching twice as many pages as it should be. That is not a sudden problem, it was a slow accumulation. And the reason it got that bad is almost always that the global auto-vacuum scale factor was too high for a table that receives constant writes. This lab walks through the diagnosis. First, check dead tuples and last auto-vacuum per table, sort by dead tuples descending and you will immediately see which tables are behind. Second, check freeze age, find how close any database is to the transaction ID wraparound boundary. Third, apply per table settings to your hottest tables. Lower the scale factor, increase the cost limit, and give those tables the attention they need without affecting tables that are fine. Vacuum full is not the answer here. Vacuum full rewrites the table, holds an exclusive lock, and belongs in a maintenance window, not in routine tuning. Bloat is a silent performance tax. When tables accumulate dead tuples faster than AutoVacuum can remove them, scans touch more pages, index locality degrades, and cache efficiency drops. The end result shows up as query latency creep. Queries that used to take 30 milliseconds now take 60, and nobody can explain exactly why. It is also worth being direct about bloat's relationship with freezing. Old transaction age is not just a maintenance nuisance. When age approaches the wraparound threshold, Postgres must take aggressive action to protect data integrity, which can mean emergency auto-vacuum runs that disrupt normal operations at the worst possible time. The most common root cause I find when investigating bloat is application transaction design. Long transactions keep old row versions visible and prevent vacuum from cleaning them up. An idle in transaction session sitting open for 10 minutes while a user reads a web page holds the horizon for the entire cluster. The query on this slide finds those sessions. When you see a transaction open for hours with a state of idle in transaction, that is almost always an application bug, not a database configuration problem. Fixing the transaction boundary in the application code is the correct fix. Lock incidents have a specific diagnosis pattern and the pattern matters. The blocked query is the visible symptom, not the cause. If you kill the blocked session, you have cleared the symptom and left the cause intact. The next session to touch that row will block in exactly the same way. The correct approach is to first identify who is waiting, then identify who is holding the lock, then understand why the hold time is so long before deciding what action to take. This lab shows all 3 steps. Finding blocked sessions, identifying the root blocker, and choosing the safest available action. Prefer pg_cancel_backend over pg_terminate_backend when possible. Canceling stops the current query and leaves the session and its transaction alive. Terminating closes the connection and rolls back the transaction, which can create visible errors for application users and needs to be done through an incident process with an owner. After the incident, always ask the forensic question, why was that lock held for 12 minutes? Was it an idle transaction? A missing index on a foreign key? A bulk migration that needed concurrent behavior? The answer to that question is where the Rail fix lives. Here is a counterintuitive truth about Postgres connections: past a certain point, adding more active connections makes the system slower, not faster. Each Postgres backend is a process. It has memory overhead for shared memory mapping, session state, and catalog caches. It participates in lock management and competes for CPU scheduling time. The throughput versus connections curve on this slide is real. At around the number of CPU cores on the host, throughput flattens. After that, latency starts climbing. I have seen systems where reducing max connections from 500 to 100 actually improve throughput and cut P99 latency, because the scheduler stopped fighting itself. A pooler solves this by sitting between your application and Postgres. It accepts thousands of client sockets but maintains a small number of actual server connections. Clients that arrive when all server connections are busy queue at the pooler, not inside the database engine. That is the key insight. Queuing inside Postgres is expensive. Queuing outside Postgres at the pooler is cheap. Size your pool by actual server concurrency, not by application socket count. And understand the semantics of your pooling mode. Transaction pooling changes how prepared statements, session variables, temporary tables, and advisory locks behave. Storage problems almost always arrive disguised as query problems. When temp bytes start growing, your first instinct might be to raise memory. But that temp growth is a symptom. The root cause might be a missing index that forced a large sort, or a query that is processing far more rows than it needs to, or a reporting job that should be isolated to a separate workload class. When P99 read latency climbs, your first instinct might be to add an index. But the root cause might be cold cache from a large table scan that a better query design could have avoided entirely. This lab runs 3 different commands: temp file statistics across databases, I/O pressure analysis, and checkpoint log review. Work through them in order. If temp bytes are high on a specific database, map them back to queries using statement statistics and plans. If read latency percentiles are elevated, correlate with buffer hit rates and plan buffer reads. If write latency spikes correlate with checkpoint timing, review checkpoint parameters and storage capacity together. Average latency is almost never the right signal. P99 is the signal users feel, treat it as first class. I want to make an argument that might surprise you. The single most impactful Postgres performance decision is often not a Postgres setting at all, it is application request shape. N+1 query patterns generate hundreds of round trips for what could be a single set-based lookup. Row-by-row inserts that should be copy commands create unnecessary index maintenance overhead for every row. Long transactions that stay open across user interactions or external API calls hold locks and keep dead rows visible. Returning every column in a table when you need 3 of them wastes CPU, memory, and network bandwidth. The database is doing exactly what it is asked to do. The problem is the question. The code examples on this slide show the pattern contrasts clearly: the N+1 loop that runs 1,000 times versus the set-based query with any. The row-by-row insert versus the copy command. The transaction that stays open across user input versus the transaction that opens at the last responsible moment and commits immediately. These are not micro-optimizations. In high-traffic systems, shifting from N+1 to set-based queries can reduce database time by an order of magnitude. Work with your application teams. Map traces to query IDs. The database performance team and the application team should be solving these problems together, not separately. Parallel query is a CPU budget allocation, it is not a free speed button. When Postgres runs a parallel plan, it creates worker processes that each consume CPU, memory, file descriptors, and work MEM. For a large analytical scan over hundreds of millions of rows, 4 workers might cut the wall time in half, and that is a good trade. For an OLTP query that returns 50 rows with a good index, the parallel setup and coordination cost exceeds the benefit by an order of magnitude, and the query actually gets slower. The problem is that the planner can sometimes choose a parallel plan when it should not, especially on tables where statistics have drifted. The approach on this slide is the safe one: test at the session level first. Set max parallel workers _per_ gather to a specific value, run the plan with analyze, and compare wall time and CPU utilization against the non-parallel version. Then check the impact on concurrent user traffic. In mixed OLTP and analytics environments, use row-level settings to give your reporting users access to parallel query without allowing them to steal capacity from latency-sensitive application sessions. Parallel query is a powerful tool when it is measured, bounded, and applied to the right workload class. Every performance change you make in production is a change management event. It needs an owner. It needs a reason, stated as a specific metric that crossed a threshold. It needs the old value and the new value written down somewhere. It needs a rollout plan that specifies whether a reload is needed or a restart, and what the expected impact window is. It needs a validation query, exactly which metric should move, in which direction, by how much, within what time window. And it needs a rollback command that can be executed by anyone on the team in under 2 minutes. That is not bureaucracy, that is how you avoid turning a slow database into a broken one. The runbook diagram on this slide shows the loop from baseline through rollback. The key insight is that rollback is not a failure mode. Rollback is a built-in option at every step. If your canary does not confirm the hypothesis, rollback and revisit. If your validation query does not show movement, rollback and reprofile. The rule I enforce on every team I work with is strict and simple: no metric, no change. No rollback plan, no deploy. Performance tuning is engineering change management with measurements. That discipline is what separates the teams that tune their way to stability from the teams that tune their way into incidents. This is the point in the session where the work becomes more dangerous, because now we are talking about parameters. A PostgreSQL parameter is not a personality trait. It is not something we tune because the server feels slow, or because a checklist said that every serious system needs a larger value. A parameter is a controlled response to a measured pressure. The slide gives you the operating model: signal, hypothesis, change, proof. If the signal is temporary blocks and external merge sorts, then we can talk about work memory. If the signal is backend writes and dirty buffer pressure, then we can talk about background writer and checkpoints. If the signal is bad estimates, then we talk about statistics, not memory. If the signal is lock weights, then no cache setting is going to save you. This is where senior database work is different from folklore. You do not tune the database by memorizing numbers. You tune it by connecting one metric to one mechanism, changing the smallest safe thing, and then proving the effect in the same workload shape. Before any parameter change goes into production, write down what should improve, what could get worse, and how you will reverse it. Shared buffers is usually the first setting people want to touch, and that is exactly why it deserves discipline. Shared buffers controls how much data PostgreSQL keeps in its own buffer cache. It is important, but it is not magic. If the query is reading the wrong rows, a larger cache only helps you read the wrong rows faster. If checkpoints are already heavy, a very large shared buffer pool can increase the volume of dirty pages that must eventually be written. On a dedicated database host, a common starting point may be around a quarter of RAM, but the number is not the lesson. The lesson is the evidence. Watch physical read latency, buffer hit behavior, eviction pressure, checkpoint write volume, and the operating system cache. PostgreSQL does not live alone. The OS cache is still part of the performance story, especially for files that are not in shared buffers and for the surrounding I/O system. A good shared buffers change should reduce physical reads or smooth repeated access without making write spikes worse. If the only proof is that the value looks more impressive in PostgreSQL config file, the change is not production tuning. It is decoration. In practice, the operator should leave this slide with 3 questions: what metric proves the pressure, what change is small enough to canary, and what evidence will convince us to keep or revert the change. Those questions keep the work honest when the room is tense and the easy answer is to guess. Effective cache size is one of the most misunderstood parameters because the name sounds like memory allocation. It is not allocated memory. It is a planner assumption. You are telling the optimizer roughly how much data is likely to be cached across PostgreSQL shared buffers and the operating system cache. That belief influences whether an index access path looks cheap or expensive compared with a sequential scan. If you understate it, PostgreSQL may avoid an index even when the working set is usually hot. If you overstate it, the planner may choose random I/O-heavy plans that look cheap on paper and collapse under real disk latency. The safe way to use this parameter is not to copy a number from a blog. Look at the host memory, the database footprint, the active working set, and the plans that are making bad choices. Then test with realistic bind values and production scale data. Effective cache size should be part of a planner investigation, not a reflex. When the plan changes, ask whether the new plan is correct under cold cache, warm cache, and peak concurrency. A planner belief that is true only during a quiet benchmark can become a production lie. Bad estimates create bad plans. That sentence is simple, but it explains a surprising number of production incidents. When explain shows that PostgreSQL expected 10 rows and found 10 million, the planner did not make a bad decision, it made a reasonable decision from bad information. Before you add another index or raise memory, inspect the estimate error. Are statistics stale after a large load? Is the data skewed? Are two columns correlated in a way the planner cannot see? Does a tenant, status, or time range predicate behave differently for different values? This is where analyze, per column statistics targets, and extended statistics become performance tools. Raising default statistics target globally is not always necessary. Often the right move is narrower, raise statistics for the columns that drive bad estimates, or create extended statistics for dependency and distinct patterns that matter to the query. The validation is visible in the plan. Estimated rows should move closer to actual rows. Join order should become less surprising. Access paths should match the real selectivity. Fixing statistics is powerful because it lets the optimizer choose the right path without forcing it with hints or compensating with unnecessary indexes. In practice, the operator should leave this slide with 3 questions: what metric proves the pressure, what change is small enough to canary, and what evidence will convince us to keep or revert the change. Those questions keep the work honest when the room is tense and the easy answer is to guess. Work MEM is dangerous because it looks small. A setting like 64 megabytes sounds harmless until you remember that it is not a server-wide cap. It can be consumed by each sort or hash operation inside each plan, across many active sessions. One complicated report can use multiple work memory allocations. One busy application can multiply that by hundreds of backends. This is why work MEM must be tuned as a concurrency budget, not as a single attractive number. The evidence is specific: external merge sorts and explain, temp blocks in PG stat statements, temp files and logs, and temp bytes in database statistics. If a known reporting query spills and the plan is otherwise correct, a local increase can be the right answer. Use set local, a reporting role, or a controlled session setting. Do not globally raise work MEM to rescue one query and accidentally create a memory incident during peak traffic. Also ask whether the spill should exist at all. A missing index that forces a huge sort should be fixed structurally. A bad estimate that creates the wrong hash plan should be fixed with statistics. Memory is powerful, but it should not hide a broken access path. In practice, the operator should leave this slide with 3 questions: what metric proves the pressure, what change is small enough to canary, and what evidence will convince us to keep or revert the change. Those questions keep the work honest when the room is tense and the easy answer is to guess. Hash memory is where the conversation becomes more subtle. PostgreSQL can use hash joins and hash aggregates to solve large problems efficiently, but when the hash table does not fit, it batches and spills to disk. In modern PostgreSQL, hash MEM multiplier lets hash operations use more than the base work MEM limit. That can be very helpful for the right workload. It can also multiply a bad decision. The first question is not whether the query spilled. The first question is whether the hash plan is the correct plan. If the estimates are wrong, if the join order is wrong, or if a predicate is missing, larger hash memory only lets the wrong plan consume more RAM. Look at batches, temp blocks, actual rows, and concurrency. If the same analytic query runs in a controlled batch window, a row level or session level setting may be safe. If hundreds of OLTP sessions can hit the same code path, the blast radius is different. Validate under concurrency, not in isolation. A hash memory change is successful when temp IO falls, query time improves, and the rest of the cluster does not pay with swap, OM risk, or higher tail latency. In practice, the operator should leave this slide with 3 questions: what metric proves the pressure, what change is small enough to canary, and what evidence will convince us to keep or revert the change. Those questions keep the work honest when the room is tense and the easy answer is to guess. Maintenance memory is not normal query memory. It affects operations like creating indexes, vacuum work, and other maintenance paths. That distinction matters because the question is not how many user queries might run. The question is how many maintenance operations might run at the same time, and what else is happening on the host while they run. A larger maintenance_work MEM can make index builds faster and reduce maintenance windows, but it can also create pressure if multiple index builds, manual vacuums, or auto-vacuum workers overlap. Auto-vacuum has its own memory behavior, and auto-vacuum_work MEM can separate worker memory from manual maintenance expectations. In production, this is scheduling work as much as parameter work. If you are rebuilding indexes during a release, what is the concurrency limit? If auto-vacuum workers wake up on several hot tables, how much memory can they consume together? The proof is not only that the operation finishes faster. The proof is that foreground latency remains stable, the host does not swap, and maintenance completes within the window. Memory given to maintenance is memory temporarily taken away from everything else. In practice, the operator should leave this slide with 3 questions: what metric proves the pressure, what change is small enough to canary, and what evidence will convince us to keep or revert the change. Those questions keep the work honest when the room is tense and the easy answer is to guess. Write-ahead log pressure is one of the places where performance and recoverability meet. Every committed change has to pass through WAL. Under heavy write workloads, that means WAL volume, FSANC pressure, archive pressure, replica replay pressure, and eventually checkpoint pressure. If commit latency rises, do not look only at SQL. Look at WAL bytes, sync time, archive lag, disk write latency, and whether replicas are falling behind. Parameters like wall buffers, wall compression, and synchronous commit can change behavior, but they are not purely performance knobs. They touch durability, recovery point objectives, replica visibility, and operational risk. WAL compression may reduce I/O at the cost of CPU. Synchronous commit choices may reduce latency at the cost of when durability is guaranteed. Larger WAL capacity may smooth checkpoints but increase recovery time. The right question is not how to make writes fastest in a benchmark. The right question is how to meet the business durability requirement with predictable latency. A WAL tuning change should be reviewed with recovery expectations in mind. If nobody can explain the restore or replica consequence, the change is not ready. In practice, the operator should leave this slide with 3 questions: what metric proves the pressure, what change is small enough to canary, and what evidence will convince us to keep or revert the change. Those questions keep the work honest when the room is tense and the easy answer is to guess. Checkpoints are how PostgresQL bounds recovery work by writing dirty buffers to durable storage. When checkpoint settings are too tight for the workload, the system can be pushed into frequent requested checkpoints. That creates bursts of write I/O and visible latency cliffs. When checkpoint settings are too relaxed, writes may be smoother, but crash recovery can take longer and storage headroom can be consumed by more WAL. The key parameters are checkpoint timeout, max wall size, and checkpoint completion target. The key evidence is in checkpoint counts, buffers written by checkpoints, write time, sync time, and the shape of disk latency during the interval. If checkpoints_REQ is climbing, max wall size may be too small for the right workload. If sync time spikes, storage may not be absorbing the flush pattern. If recovery objectives are strict, you cannot simply stretch everything forever. Tune checkpoints as a balance between write smoothness, recovery time, and disk capacity. A good checkpoint change makes latency flatter without making the recovery story unacceptable. That is why this topic belongs in the production section, not just the performance section. In practice, the operator should leave this slide with 3 questions: what metric proves the pressure, what change is small enough to canary, and what evidence will convince us to keep or revert the change. Those questions keep the work honest when the room is tense and the easy answer is to guess. Background writer tuning is about reducing surprises for foreground backends. PostgresQL has to write dirty buffers eventually. If the background writer does not clean enough reusable buffers ahead of demand, user backends may be forced to write buffers themselves. That is visible as buffers backend in pgstat-bg writer, and it often appears during latency spikes where application sessions are paying for write work they did not expect. The parameters are background writer delay, background writer LRU max pages, and background writer LRU multiplier. But do not start by changing them. Start by reading the story: buffers clean, max written clean, buffers backend, checkpoint writes, and the workload pattern. If max written clean is frequently hit, the writer may be capped. If buffers backend is high, foreground sessions are doing too much cleaning. If checkpoint writes dominate, the issue may be checkpoint configuration or storage throughput, not background writer alone. The background writer complements checkpoint tuning, it does not replace it. The goal is to smooth dirty buffer recycling so fewer user transactions hit sudden write work. Backend writes are a latency smell. Treat them as evidence, not as trivia. In practice, the operator should leave this slide with 3 questions: what metric proves the pressure, what change is small enough to canary, and what evidence will convince us to keep or revert the change. Those questions keep the work honest when the room is tense and the easy answer is to guess. Storage tuning starts with measured latency, not with brand names or assumptions. PostgreSQL can be perfectly tuned at the SQL layer and still suffer if storage cannot sustain the mix: random data reads, WAL syncs, temp file writes, checkpoint flushes, backups, and archive traffic. You need database evidence and host evidence together. Data file read weights, temp bytes, WAL sync time, checkpoint sync time, queue depth, and latency percentiles should all tell a coherent story. Separate paths where possible. WAL has a different latency sensitivity than large sequential backup traffic. Temp files have a different pattern than random index reads. A benchmark on empty storage is not proof that the production mix will hold under pressure. Also watch for noisy neighbors, cloud volume burst credits, file system behavior, and encryption overhead. The validation question is simple: when the database says it is waiting on I/O, does the storage layer show the same pain at the same time? If not, keep investigating. The most expensive storage mistake is buying capacity when the actual problem is latency, or buying latency when the actual problem is query shape. In practice, the operator should leave this slide with 3 questions: what metric proves the pressure, what change is small enough to canary, and what evidence will convince us to keep or revert the change. Those questions keep the work honest when the room is tense and the easy answer is to guess. Auto vacuum is a performance feature. It is the mechanism that keeps dead tuples from becoming table bloat, keeps statistics fresh enough for the planner, and protects the database from transaction ID wraparound. Defaults are intentionally general. They are not a promise that every hot table will be maintained well. Large tables with small percentage churn can accumulate millions of dead tuples before a scale factor threshold fires. Hot tables can need more frequent vacuum and analyze than the database-wide defaults provide. Use table-level settings: auto vacuum vacuum scale factor, auto vacuum vacuum threshold, analyze scale factor, cost limit, and cost delay. Watch end dead tuple, last auto vacuum, vacuum count, analyze count, and rel frozen xid age. The goal is not to make auto vacuum invisible. The goal is to make it predictable and early enough that it prevents bigger incidents. If auto vacuum is always behind, queries get slower, indexes get fatter, cache becomes less useful, and maintenance becomes more expensive. A tuned auto vacuum setup turns cleanup into routine background work instead of emergency surgery. In practice, the operator should leave this slide with 3 questions: what metric proves the pressure, what change is small enough to canary, and what evidence will convince us to keep or revert the change? Those questions keep the work honest when the room is tense and the easy answer is to guess. Freeze age is not an obscure internal number. It is a countdown to forced maintenance if ignored. PostgreSQL must eventually freeze old transaction IDs so visibility rules remain safe. Long transactions, idle and transaction sessions, replication slots, and underpowered vacuum settings can all push the system toward danger. When freeze age climbs, the database may need aggressive vacuum work that competes with production traffic at exactly the wrong time. The first fix is often not a parameter. It is finding and removing the transaction horizon that prevents cleanup. Look for old transaction start values, idle sessions, long-running reports, and replication slots retaining old data. Then tune vacuum cost behavior and table-specific settings so cleanup can keep up without overwhelming storage. Cost delay and cost limit are not morality settings, they control how aggressively vacuum spends I/O. Too gentle and you fall behind. Too aggressive and foreground latency suffers. The right balance is measured by dead tuple trend, freeze age trend, and user-facing latency during maintenance. A long transaction can turn normal maintenance into a performance incident. In practice, the operator should leave this slide with 3 questions: what metric proves the pressure, what change is small enough to canary, and what evidence will convince us to keep or revert the change? Those questions keep the work honest when the room is tense and the easy answer is to guess. Removing bloat is an operation, not just a command. Once tables and indexes are bloated, ordinary vacuum may stop the bleeding, but it will not always return space or reduce structure size. The remediation choices have different risks. Vacuum full rewrites and locks. Cluster can restore physical order but requires planning. Reindex or reindex concurrently can help bloated indexes. PG_repack can reduce blocking but brings its own operational requirements. Partition rotation can be the cleanest answer for time series data. The choice depends on availability, disk headroom, replication lag, backup impact, and how much blocking the application can tolerate. Before action, quantify the problem: table size, index size, dead tuple trend, scan cost, cache pressure, and the queries affected. During action, monitor locks and disk growth. After action, prove that relation size fell and query reads improved. Do not run a dramatic cleanup command because a dashboard looks ugly. Run it because the bloat has a measured cost and the operation has a rehearsed safety path. In practice, the operator should leave this slide with 3 questions: what metric proves the pressure, what change is small enough to canary, and what evidence will convince us to keep or revert the change? Those questions keep the work honest when the room is tense and the easy answer is to guess. Timeouts are guardrails for bad concurrency days. They are not a substitute for good schema changes, short transactions, and correct application behavior, but they keep one blocked path from turning into a full outage. Lock_timeout can prevent a migration from waiting forever behind production traffic. Statement_timeout can stop runaway queries from consuming capacity indefinitely. Idle_in_transaction_session_timeout can protect the system from sessions that open a transaction and then disappear while holding locks and old snapshots. These settings should be scoped carefully, per role, per application, per migration tool, or per session where possible. A global timeout without application handling can create noisy failures. A migration timeout without retry logic can leave deploys half complete. The workflow is to observe blocking chains, identify the blocker, choose the least destructive action, and then add guardrails so the same pattern fails safely next time. Timeouts are most valuable when they turn a mysterious hang into a controlled error that the system and operators know how to handle. In practice, the operator should leave this slide with 3 questions: what metric proves the pressure, what change is small enough to canary, and what evidence will convince us to keep or revert the change? Those questions keep the work honest when the room is tense and the easy answer is to guess. Connection count is a performance parameter. Every PostgreSQL backend consumes memory, scheduler attention, and potential lock participation. When thousands of clients connect directly, the database can spend too much time context switching and managing concurrency instead of doing useful work. A pool is a pressure valve. It queues excess work before it enters PostgreSQL, where you can control fairness and protect tail latency. Size the pool from CPU cores, active query time, transaction length, and latency objectives, not from the number of web workers that would like a connection. pgbouncer transaction pooling can be excellent for short OLTP paths, but session pooling may be needed when application state, prepared statements, advisory locks, or session settings require it. The proof is lower active backend count, steadier CPU, less memory pressure, and better P99 latency under load. If the pool is too small, the application waits unnecessarily. If it is too large, PostgreSQL becomes the queue again. The goal is not maximum connections. The goal is maximum useful throughput at acceptable latency. In practice, the operator should leave this slide with 3 questions: what metric proves the pressure, what change is small enough to canary, and what evidence will convince us to keep or revert the change. Those questions keep the work honest when the room is tense and the easy answer is to guess. Sometimes the fastest database fix is changing the shape of the request. PostgreSQL can execute efficient SQL very well, but it cannot make unnecessary work disappear. N+1 query patterns, unbounded pagination, selecting wide rows when only 2 columns are needed, keeping transactions open across network calls, and returning huge result sets all create database pressure that no parameter can fully hide. Measure database time per request, not only individual query latency. Count calls per page load. Look at rows returned versus rows used. Watch transaction age from the application path. Then fix the shape, batch lookups, use keyset pagination, narrow select lists, shorten transactions, and move non-critical work out of synchronous request paths. This is where database tuning becomes application architecture. The database team and application team need the same evidence package. If the application generates 100 tiny queries for a single user action, tuning shared buffers is not the strategic fix. Do less work first. Then ask PostgreSQL to do the remaining work faster. In practice, the operator should leave this slide with 3 questions: what metric proves the pressure, what change is small enough to canary, and what evidence will convince us to keep or revert the change. Those questions keep the work honest when the room is tense and the easy answer is to guess. Parallel query is a CPU budget decision. It can make analytic scans and large aggregations finish faster by spending more CPU at once. That is useful when the system has headroom and the target query matters. It is dangerous when the cluster is already serving high concurrency OLTP traffic and every extra worker competes with user requests. The parameters include max parallel workers _per gather, parallel setup cost, and parallel tuple cost. But again, the parameter is not the starting point. The starting point is whether the query is truly scan or aggregate heavy, whether the plan is using workers effectively, and whether cluster-wide latency stays healthy when those workers are active. A query that gets faster in isolation can still be a bad production change if it steals CPU from thousands of small transactions. Validate both the target query and the system around it. Parallelism is not free. It spends CPU faster. Use it where spending CPU faster is exactly the trade-off you want. In practice, the operator should leave this slide with 3 questions: what metric proves the pressure, what change is small enough to canary, and what evidence will convince us to keep or revert the change. Those questions keep the work honest when the room is tense and the easy answer is to guess. A tuning change is not complete until rollback is rehearsed. This is where many teams are too casual. They debate the parameter for an hour, apply it in production, and only then discover that nobody knows whether a reload is enough, whether a restart is required, which dashboard proves success, or how long to wait before reverting. A production-safe change has a canary plan. Maybe it is 1 role, 1 application slice, 1 database instance, or 1 time window. It has success criteria: P95, P99, error rate, wait events, temp bytes, WAL pressure, memory, locks. It has failure criteria. It has an owner watching the window. And it has an exact rollback path written before the change starts. The discipline is not bureaucracy. It is how you move quickly without gambling. If the canary proves the hypothesis, expand. If the metrics are mixed, pause. If the failure criteria appear, revert. The safest tuning culture is boring, measured, and reversible. In practice, the operator should leave this slide with 3 questions: what metric proves the pressure, what change is small enough to canary, and what evidence will convince us to keep or revert the change. Those questions keep the work honest when the room is tense and the easy answer is to guess. The final operating model is a scorecard. Not because scorecards are fashionable, but because performance tuning has to become routine. Every week, review top statements by total time, mean time, temp writes, and rows processed. Review weight profiles. Review dead tuple growth, bloat candidates, old transactions, and temp file volume. Every month, review index usage, overlapping indexes, parameter changes, pool sizing, storage headroom, and checkpoint behavior. Before major releases, benchmark the changed path and document rollback. After incidents, record the signal that would have caught the problem earlier. This turns performance from hero work into operating discipline. The goal is not a perfect PostgresQL config file. The goal is a team that can prove every tuning decision, explain every trade-off, and improve the system before customers feel pain. A mature PostgresQL team does not tune by superstition. It measures, classifies, tunes the smallest safe layer, proves the result, and keeps the evidence for the next decision. In practice, the operator should leave this slide with 3 questions: what metric proves the pressure, what change is small enough to canary, and what evidence will convince us to keep or revert the change. Those questions keep the work honest when the room is tense and the easy answer is to guess. The 4 words on this slide are the entire session reduced to a method. Measure first statement statistics, wait events, plans, logs, storage percentiles. Classify the bottleneck CPU, I/O, lock, spill, or application shape before you choose a fix. Tune the smallest safe layer, query before index, index before global parameter, table setting before cluster setting, local proof before cluster change. Prove the outcome before and after numbers, defensible comparison window, rollback ready. Postgres performance tuning is not a set of magic configuration values. Every parameter interacts with your specific workload, your specific data distribution, your specific hardware, and your specific application behavior. The teams that do this well are not the ones with the longest list of parameters to adjust, they are the ones who measure patiently, classify carefully, change minimally, and prove everything. Thank you for joining Dr. Ibrar Ahmed for this session. Take this method back to your team and use it next time something goes wrong. The expanded message is this: PostgreSQL performance tuning is not a bag of tricks. It is an engineering operating system. Measure the workload. Classify the bottleneck. Tune the layer that the evidence names. Prove the result in the same workload shape. Keep rollback close. If you follow that discipline, parameter tuning becomes safer, query tuning becomes more focused, and production incidents become less mysterious.